All right. Good morning, folks. Hope everyone's doing well this morning. Let me go ahead and get started with the lesson here. What I would like to do today then is I'm going to go ahead and like I told you yesterday, I want to go ahead and finish up with the projectile motion problems. We'll finish up working through number 4. We started that yesterday. That was number 4 from page 152. That was your homework from that was due last night. That was due last night. That was assigned a week ago. Okay, so I'd like to go ahead and finish up that problem for you. And then I want to go ahead and I want to work through a second type of projectile motion problem, and then try to finish up with projectile motion. And today start with the centripetal motion, or that is the circular motion, and work through those types of problems there. Okay. So with that said, then let's go ahead then and let me go ahead and share this with you. So let's take a look at number 4 from our problem from the homework. And we started working through this problem yesterday. And in number 4 here, what they ask us for is they ask us to solve for first the total time. Then they want us, or find the total time. They want us to find the height, which is the maximum delta y, the maximum vertical distance. And they want us to find the range, which is the maximum horizontal distance. Okay? So we were able to work through yesterday, and we were able to find them the total time. And remember, the total time is the same. When we say total time, it is basically the time that the object spends in the air. Okay? And the total time the object spends in the air is going to be equal to, is going to be the same as the time it takes to get from x initial here to x final. So the total time it takes for it to travel the total horizontal distance is the same amount of time that it's going to take to spend in the air. Okay. All right. So with that said, then we were able to solve for it. I solved for it one way here. I solved for it for the previous problem. I solved using a slightly different method to also try to find that total flight time. Either way works. Okay. Either way works. Whatever way works out better for you, that helps you understand. Please go ahead and use that method. Okay. So in this particular method here, what I did was then find the total time. I said then that the total time then represents the time it takes to get from the start here along the vertical and then back to that position. Okay. So therefore, then we're going to look at the initial and the final velocities at that position. And remember, we're going to look at this in the vertical direction. Okay. So we want to see then, and we want to make sure we remember then that distance, that velocity. If we look at this pathway here, it's symmetrical. And so the velocity up and the velocity down, that is the vertical velocity in both directions. Okay? I'm sorry, the vertical velocity at both positions. Okay? We said then that the magnitude will be exactly the same, but the direction will be in the opposite direction. Okay, and that's what I took advantage of here. So my V initial then will be here, V initial on the Y, and my V final on the Y will be right here as well. Now we know what V final on the Y is because, again, based on what we know about this type of motion here, that this is symmetrical motion. And so therefore, the velocity initial and the velocity final here will be exactly the same, except for they'll be in the opposite direction. Okay. Now we know then that the velocity along the X will never change. So that always stays the same from start to finish. Okay. But what does change is the direction of the Y, the velocity in the Y direction. Okay. And so what will happen then is we solve for the velocities and the X and the Y component of the initial velocity. We're going to take the final velocity at this point then, and it's going to have that magnitude. It's going to have a magnitude of 13.5 meters per second, but it's going to be the opposite direction. And that'll be our V final. And so if you take a look at this here, then I took the kinematic equation. I took the second kinematic equation here. And on the exam or on the quiz, folks, I'm not going to ask you to memorize these. It's probably going to benefit you to memorize these anyway, but I'm not going to ask you to memorize these. And so I will give them to you. But what I cannot do, I can't tell you which one to use. And so with that said, then, if you notice here, if you go through the list, then we want to find the ones with time in it. We have the first one obviously will not give us time, so we don't want to use that. But we have these other ones here. Okay? And so what we learned back in chapter 3 is that we choose the equation then that will give us our unknown, but we also have all the other variables available as well. Okay, so the second equation here, we have V final. That's not this one now. This V final is not the same as the one we're going to use. We need V final Y. Okay, and so we have that. Okay, we have V initial Y, and then we also have the acceleration. okay, which is going to be negative 9.8 meters per second squared. So we have everything we need to solve for the time. We plug it in here, and making sure then that you remind yourself that you got to include the directions of these vectors as well, because if you don't, you end up having getting 0 in the numerator, and you end up with the time as 0, which doesn't make any sense. Okay, so you got to make sure then that you include in the correct sign, correct direction, or else you will get this problem wrong. Okay, all right. So with that said, then you get that done, and then you get your answer then as 2.76 seconds. So that's the total flight time. So what I would like you to do now is on your paper to get started out with this one, to get started with this. So hopefully this will give you some practice with working this out. Okay. So what I'd like you to do is on your paper here, I would like you to work out B and C. In B, then they want you to find the height, which is we're going to call delta y. Okay, so that's delta y at the maximum height. So let's call it delta y max. Okay, so solve for that one, and then for C, they want you to find the range. So on your paper, let's take about 3-4 minutes. Hopefully, it doesn't take you that much longer. But let's take about 3 or 4 minutes to work out these two problems here, and then after you're done, go ahead and unpause the video, unpause the video, and let's compare answers. Okay, so let's take about then 3 minutes, 3-4 minutes. If you need longer, then go ahead and do so. But take about 3 minutes to solve then for the height and for the range. Okay, so make sure you understand then that what they're asking you for here, this is what we refer to as the height. Okay, that's how high up it goes, and this is referred to as the range. Okay, so go ahead, calculate for the height and the range. Let's come on back, and then let's compare answers. Okay, so take about 3 minutes to get this done. Okay, all right. So let's deal with the height first. Okay? Now, height is on the vertical. So remember, with the vertical, then you're going to use any one of these equations. Now, again, in these kinematic equations, I've written it so that it is delta x, the horizontal distance. But remember, all these then can be converted or changed to motion along the y by just simply changing the variables. Okay? So we want to find then displacement. That is, in what we're going to solve here is delta y. Okay. So the first equation gives us delta y. It absolutely does. And if you take a look at it, what we need then is v final, the initial, and the acceleration. Okay. If you look at what we have here, okay, and remember, we're trying to find this distance up here. That distance it takes to go up here. So the way that you would imagine this then is, if we can take this object and stop it right there, pause its motion. Okay? And so that means then we want to examine this first half of the pathway here, the upward trajectory, which means then we want the final, this would represent then the final velocity at this point here. So we stop right here, that would be final velocity. We know what the initial velocity is. So with that said then, when we work through these problems here, we have the final velocity. We have the initial velocity. We have the acceleration. There it is. We can go ahead and solve for delta x. So we can go ahead and use that equation if we wanted to solve for delta x, for the displacement. Okay? And we can do the same thing here. Okay? To solve then for the displacement, okay, we would need then v final. And again, that v final would be this point at the very top of the pathway here. We know what v initial is in the y, and we just solve for time. So that would work as well. And then finally, if you take a look at the last equation, we have the initial along the y. We have solved for the time as well. We can go ahead and use that to solve for this one. And then we have the acceleration as well. Okay, so any one of those would work. I think probably the easiest one to work through, use then would be this one. But I want to use, let me go ahead, I'm going to use this one right here. For one purpose then is that's to see then how we would determine the time interval here. So you got to be careful. We did calculate for the time here, but this is the total time. That's the time it takes to go up and then back down. So if we're going to use this equation here, we have to be careful about what we plug in for the time interval. So let's go ahead then and let's work that out. Okay. And so we would do the same thing if we're going to use this equation as well, the third one. Okay. All right, so there it is. So let's go ahead and plug this in. We have done delta y. It's going to be equal then to v initial in the y direction times time plus 1/2 acceleration in the y times t squared. Okay. Let's go ahead then and let's plug in some values. Delta y, we have it right here. V initial then along the y is 13.5 meters per second. Okay. Now the question then is, what's the time interval? Is it 2.76 that we're going to plug in right here? And you got to be careful because the answer there is no. We're not plugging in 2.76 because remember, this is the time it takes to go up and then come back down. To get this vertical height right here, we just need to know then the time it takes to go up. And the time it takes to go up, remember, is half the time. And so let's go ahead and do this. So let's come right to this. It's going to be half the amount of time it takes to make the total trip. Okay, which means then this is going to be 1.38. And we know it's half. Why? Because the time it takes to go up and the time it takes to go down are exactly equal. Okay, they're exactly equal. So therefore, then, if we know what the total time is, find the time of the time it takes to go up, we just take half. Take half of the total flight time. So there it is. That's the time that we're going to use, not 2.76. Okay, so let's go ahead and let's plug that in. We have then 1.38 seconds. Okay, plus, and I'm just gonna quickly write this down here, you guys. 1/2. A, remember, is A along the y is negative 9.8 meters per second squared. And don't forget that sign, folks. If you do forget that sign, your answer is going to be larger than it should be. Okay? And then again, the time then is going to be 1.38 seconds. We'll square that. Okay? All right. So you plug that in then, and I get an answer then is 9.30 meters as the vertical distance. That is how high up the football here, the ball here, flies up into the air. That's the height right there. Okay. Now, if you plug in and you had chosen the very first equation, if you had chosen this one, you should get the exact same answer. That it should be no different. Okay, it should be no different. With this one, then I think between what I did here and the first one, I think using the first equation is a little bit easier because we find out there is going to be 0. So you just go ahead then and you can rearrange the equation to solve for this problem. Okay. All right. Now, so make sure you compare your answers and see what you get. Okay, let's go ahead and let's solve then for the range. Okay. To solve for the range, which is the horizontal distance, okay, this becomes very simple because there's only one equation that we have. There's only one equation that we use to solve for anything that occurs along the horizontal. Because remember, along the horizontal, there's no acceleration. The velocity is constant. Okay? And so therefore, to find the displacement, we're going to go ahead then and we will use that equation. And that's the one I have listed for you right here. So finding then the range, which is the motion along the x, we need v initial x, and we need the total time now. Because like I pointed out, the total time is the time it takes to get from the start here to the finish. Okay, so this equation we're going to use then to solve then for delta x. V initial x here we have then is 23.4 meters per second. Okay. And the time interval here we're going to use is 2.76 seconds. Excuse me. Okay. And so make sure then, and I want to make sure you folks understand this. Y for B, we used 1.38 seconds as time. And then for C, we end up using 2.76. You got to make sure you understand and remember why we were going to do it that way. Okay, so if you're unclear, please make sure you come by and I'll explain it to you again. Okay. All right. So plugging that in, this becomes pretty simple. This the answer then becomes 64.5 meters. Okay. So I think the more you practice these problems, the better you get at them. The more likely you'll be able to pick up on the subtle differences between one problem and another, and also you'll be able to work through those differences. Okay, so please come by and see me if you're not quite sure then how I work through this, because sometimes folks, and I had this discussion with a couple of folks already this semester, and that is, and last semester I should probably point that out, that I've taught this a long time, and so sometimes I make assumptions about what you folks, the abilities that you folks have, and I assume that you know something, and then I skip that step where I move on to the next step, assuming that you already know. If there's something that I do here when I solve these problems, there's something that I do that didn't quite click for you, or you're not quite sure how I got that. Again, like I pointed it and when I met with some of you folks, I said, as you watch these lessons, and it's good practice anyway. Okay, you should write down questions. So if there's something that I did here that didn't quite click for you, or you didn't quite sure how I got that, just write that down. No matter how simple, no matter how silly, I would suggest you write it down, then you ask. Okay, because sometimes, like I said, if that it may be just a minor issue that I can help you resolve, and then it clicks for you. Okay, so the challenge, I think, I'm not going to make it mandatory, but the challenge, I think, for you then is to try to at least write down one question per assignment, and then and then try to get your questions answered. Okay? Now, if you can answer it yourself afterwards, that's fantastic. It means you really do understand the concept. But if you don't, that's what I'm here for. Okay, so please come by and get your questions answered. Okay, let me go ahead and save that. Let me clear that out. Okay. And what I'd like to do now then is I would like to, whoops, where is it? Whoops, hold on one second here. I would like to talk about one more type of motion here. Whoops, sorry, not that one. Where'd it go? Nope. Okay, there it is. Okay, I want to talk about one more type of motion. And it is projectile motion. So let me go ahead, and I'm going to use in here the FetLab, okay, to help me demonstrate this next type of motion. Okay, so let me go ahead and move this over. Whoops, sorry. Move this over here really quickly. Okay, and share it with you. Okay, so let's go ahead and let's take a look. So this is the FetLab that you did. Okay, and so what we've been examining, and again, I clicked off air resistance here. I'm going to click velocity vectors here and components, because what we've been doing then is we've been taking an object and we've been shooting it from the ground basically here. We shoot it up and then it comes back down. So I'm going to go ahead and do this really quickly here. So this is what we've been told. Okay, it leaves the cannon, and it has these two components of the velocity vector. Okay, so remember, with the components of the velocity vector, we have the x and the x and the y, and we notice then that as we progress, the x component stays the same, but the y component will change. We saw that as well. And then as it's and at the very top there, let me go ahead and pull it back just a little bit here. Whoops, sorry. Anyway, at the very top then, what you should have seen then is that at the very top, you only have the horizontal component. You only have the horizontal component shooting out and away. Okay. And as it starts to move past that peak point, then it starts the velocity vector, the y component of the velocity starts to get larger and larger until it just touches the ground, and right before it touches the ground, it has reached the fastest point it's traveled along the vertical. Okay. All right, so that's the parabolic motion. That is what we call projectile motion. However, and let me go ahead and do this here. Projectile motion can also be we can also consider projectile motion an object being moving in projectile motion if, let me go ahead and do this here. If we take the object and we push it up on a cliff, we put it up, we elevate it, we move up our object here, and then what we can do is we're going to launch it from this point. We're not going to launch it from the point on the ground here. So we're not going to launch it at the point on the ground. We're going to raise our platform here above the ground. So here we've raised the platform. Let's just do there it is. So we raised the platform up a distance of 10 meters above the ground. Okay, and then I'm going to go ahead and do this really quickly. Okay, remove air resistance. We got the velocity vector. We got the components in there. I'm going to go ahead and launch the rocket. Okay. Oops, sorry. Let me backtrack here again. Let me try that again. Whoops. I'm going to slow down the speed here. Sorry, guys. Let me reset that. All right, let me go ahead and reset that. We have this 10 meters right there. Okay, set that at an angle of 0 because you want to shoot it. Now, from up top here, you can also shoot it at an angle. You can even shoot it at a negative angle here. The negative angle, remember, just puts in the 4th quadrant. But I want to leave it at 0 right now. Okay, so I'm just going to shoot it straight out. Okay, and I'm going to see if I can time it. Okay, right there. And it already started then. But whoops. Okay, let me try it again. I want the components in there. Okay, let's shoot it. Okay, well, oh, come on. Oh, this is really frustrating. All right, let me try one more time. Okay, now I'm going to add in the vectors right here. Okay, and what you're going to notice here is when you first shoot it out, and let me see if I can do it one more time, folks. I want to see if I can get it just perfectly for you. Okay, right there. It didn't stop again. Sorry. One more time. This is so, and I got it to work. Sorry, guys, I got it to work. Okay, well, okay, we'll just work it from there. Okay, let's pretend that it's just being shot out of the cannon here. So it's just being shot out of the cannon. And what I'd like to draw your attention to first and foremost is this velocity vector right here. Okay? And I want you to just imagine then really quickly that it hasn't started its downward turn yet. But if you look at this, right at the initial, right when it's being shot out, the initial velocity here, okay, the initial velocity here is only horizontal. Okay, so the initial velocity, and this is not the initial velocity at an angle. You only have an x component. Again, let's try ignoring this for right now. Let's ignore this for right now. Let's pretend that I just shot it out of the cannon, and before it starts its downward descent, you notice then that the initial velocity is strictly along the horizontal. There is no vertical component to this. Why is that? Well, you can imagine what's happening here is that we are, if you can imagine then that we trace the parabola here. Okay? You can imagine then that what we're dealing with here, and I'm going to try my best, and that's really bad right there. You can imagine then that what we're doing here is that we are essentially taking the cannon here and we are moving it up to the very height of that pathway. What we're doing then is that we are looking only at the downward trajectory here, and we are going to ignore the upward part of the projectile motion. So this is still projectile motion, guys. This is still projectile motion. But what we're going to do then is by elevating the platform here, we're going to ignore the upward trajectory. So this upward trajectory here, as it moves up, we're going to ignore that because all it's going to do now, it's not going to move up because we've already elevated. We have already moved it up to that very top spot. Okay, so that means that when we fire out the object here, because we are at the maximum height here. Okay? Remember, V max along the y is 0 meters per second. Okay? And then therefore then, at the V max here, we only have the x component. So this is right when we fire out the cannonball. Okay, we only have velocity along the y, and that's it. Now, as I unpause this and I continue to let it to go, as I unpause it, okay, and the pause again, what do you notice happening? First of all, and this is going to be Vx, and let me go ahead and label this now again. So this is going to be then the velocity. This is no longer initial velocity. This is velocity along the x. Okay, this is velocity along the x. Okay, but at some other time t. Okay, so that is what we have. But if you notice here, we're starting to see then velocity along the y direction, and it's starting to grow, and it's going to get larger and larger. And we'll call this Vx at position 1. Okay, and this is Vy at position 1. Okay, and so as we allow it to progress. And whoops, sorry. Okay. And as we allow it to progress, I'm going to do that. Okay. Okay. You're going to see then that at this position here, and we'll call this Vx2, and this is Vy2. Okay. You're going to notice then x still stays the same, but the velocity along the y starts to get larger and larger. It gets bigger and bigger. as we progress downward. Okay, so let's go ahead and let's unpause it and see it at another point position. Oops, sorry, let me go do this. Okay, I'm gonna pause it right there. All right, again, I want to draw your attention to, if you take a look at this, this is velocity along the x at some position 3 now, okay? And if you notice, it still stays the same. And then finally here, the velocity along the y at position 3 is going to be larger. So that velocity along the x, x velocity at 1 is going to be equal to the x velocity at position 2. It's going to be equal to the x velocity at position 3. The velocity along the x does not change. That's still this. So this is still projectile motion. But if you notice, okay, velocity along the velocity 1 is going to be less than velocity at point 2 along the y, which is going to be less than velocity at position 3 along the y. And we know this because why? The object accelerates in its downward trajectory. That means that by the very time right before we hit the ground, that's when we will get the greatest velocity, that we have here. Okay? All right, so you got to keep this in mind. When we do this type of problem here, where we take an object and we take the launcher and we take everything and we elevate it and then we launch it outward. Okay? That's still projectile motion. Has the exact same characteristics of projectile motion, where the velocity along the x is constant. Why? Because the acceleration along the x is 0, and the net force along the x is going to be 0. The reason why the velocity gets larger and larger is because the acceleration along the y is g. We have that acceleration, and that the sum of the forces along the y, then we only have one, and that's going to be gravitational force. So even though this motion doesn't, and I still think it looks like motion, as it's just we're looking at the downward trajectory, and that's what we see right here. Okay, so when we are shooting an object off a cliff, even, or any object elevated above the ground, okay, it is still considered projectile motion, but this time we're only looking at the downward, not the upward trajectory. We're only looking at the downward trajectory here, and that's all we want to focus in on as we work through this. Okay, so we want to focus on that downward trajectory. Okay, so how would you know when it's this type of problem here? Well, you read the problem and you identify it. Okay, so let me go ahead and save this here. Okay, and let's go ahead then and let's take a look at a problem then that asks you to do just this. Okay, so let me go ahead and go do that. Okay, all right. So let's go ahead and let's take a look at this problem here, and let's work this one out together. And so this is number 6 in your problem set. So grab your problem set. Let's work this one out together. So make sure you write down what we do here. So let's go ahead and let's take a look at this. Okay. All right. So we have then a stone that's going to be thrown horizontally off a cliff. Okay, that is 78.4 meters high. Okay. So what you would do then, and what I would suggest you do is again sketch this problem. Sorry. Let's go ahead. Let's sketch this problem here. Okay, let me go and sketch that. So I always start my sketch then with, and I always do this, with the surface of the earth. Okay, so let's go ahead and draw that. Okay, there's the surface of the earth right there. Okay, now the difference here then is what we do with this particular problem then is that we elevate, we take our object and we are launching it not from the surface of the earth, but we're launching it from a position that is above the surface of the earth. And how much above the surface of the earth are we with this particular problem here? So that's this distance right here. That's how high up it is. Okay. And we were told then that it is starting at a position that is 78.4 meters, okay, above the surface of the earth. So this bottom line down here, this is the surface of the earth. This is the earth of the earth. Okay, and this is our elevated position here. So this is our elevated position right here. And how high up off the surface of the earth do we elevate it? We have elevated it 78.4 meters above the surface of the earth. Okay, so we have our stone. So I'm going to go ahead just real quick here. I'm going to draw our stone. Okay. And let's pretend that we have it right here. Okay. So our stone then starts out at the very top here. So it's starting at the upper part of the trajectory. Okay. And then what we're going to do then is we're going to launch it out. And then we know then that what happens is it's going to land somewhere down on the surface of the Earth. Okay. So there it is. We have a projectile motion problem, but we're going to look at the downward trajectory. Okay. All right. So we were told then that the stone then is thrown horizontally, because we have then a horizontal. So it's going to be thrown, and let's write in the velocity vector here. Okay, so it's thrown directly horizontally, okay, at a speed of, so this is the initial velocity now, okay, of 5.0 meters per second. Okay. Now, what you're going to notice then is as we progress downward, that velocity obviously is going to start transitioning. It's going to change so that it's going to eventually hit the bottom with a certain speed. So the red arrows then represents then the velocity. Now, I'm sorry, obviously it's going to increase as we go along. Okay, but what you notice here then is we want to find the components. We want to find the components here. So let's go ahead then and let's identify the components of the initial velocity. So let's identify the components of the initial velocity first. Okay. And if you notice here, whoops, where's my marker? Oops, sorry. Okay. Let's go ahead then, let's find the initial velocity. Okay. So the initial velocity, okay, along the x is going to be 5.0 meters per second. The initial velocity along the y here then is going to be 0 meters per second. Remember, that's at the very top. That's at the very top of the pathway there. Okay. All right. So that we know. That we already know. We also know then, let's make sure we keep this in mind then. We know then that the acceleration along the y is going to be negative 9.8 meters per second squared. And then finally, we do know one other piece of information here. Okay. And that is, what is the vertical distance? Well, how far does the object fall? What is the displacement of the object in the downward trajectory? And it's that right there. Okay, the height of the cliff then represents then how far it falls. And this has to be negative here because it's falling downward in the negative direction. So we know then delta y, we know what that is. We know the displacement. We know the acceleration. We know the initial velocities on the x, initial velocities on the y. And remember, I told you that's something you got to make sure you do when you draw these pictures. Make sure then that you label your picture. Okay. All right, that's everything that we know. That's everything that we know. I'm sorry, we do know one other thing, and I apologize here. Okay. We know then the final velocity along the x. Why do we know that? Because the velocity along the x never changes. So therefore, then if the initial velocity along the x here is 5, the final velocity along the x here will also be 5. And that's everything that we know about this motion so far. Okay. All right, so what do they find? What do they want us to find? Okay, they want us to find the total time again. So they want us to find t total. This time, though, t total represents the time it takes to hit the ground from the very top here. So it's going to be the time it takes to go the downward trajectory. Okay, so they want us to find that first. Okay, so that's what they want us to find. And then they want us to find okay, how far from the base of the cliff. So they want us to find the range, which is delta x. Okay, so they want us to find this distance right here. Okay, so they want us to find the range. Okay, and then they want us to find then the horizontal and vertical components of the stone's final velocity right before it hits the ground. Folks, we already solved it. We already have right there, and we've already done this. We have the x component right there without having to calculate for anything, folks. We found then the x component of the final velocity. All we need to do then is find the y component for that final velocity. Now, once you have that, you can actually find the final velocity using the Pythagorean theorem, and you can find the angle at which it's going to strike the ground. That you can just use the inverse tangent function. Okay, so but they don't ask for that here. Let's go ahead then. Let's continue on. Okay. All right. So first things first, let's go ahead and let's solve for time. Okay. Let's go ahead and solve for time. Okay. And I'm just going to solve it right here. All right, so t total then, what we're going to do then is we're going to use the kinematic equations. We're going to use the kinematic equations in order to solve for this. Okay? All right, so with the, if we take a look at this, then we want to solve for time, which means then we want one of these three equations here. Okay. If you take a look at the first one here, ask yourself the question, do we have the final y? Do we have the final velocity along the y? And right there, you can stop because no, that's something we have to solve for. That's one of the unknowns in this variable, in this equation. So we can't solve for that one. Okay. And the same thing holds true then for the second equation, for this third equation here. We need that v final along the y. And again, we don't have that, which leaves us only one option here. And that is to solve then for the time. We need to look at the third equation here, okay, and see if we can work it out that way. Okay, so let's go ahead then and let's write it out. So to find the total time then, we're going to use then delta y going to be equal to v initial along the y times time plus 1/2 acceleration along the y times t squared. Okay. All right. So do we have, so with that said, then we're going to solve for time. Now, before we, and this is where I kind of make an exception to my rule of always solving then for the, I'm going, of solving then for the, rearranging the equation to solve for the unknown first. And the reason, and I know I'm going a little bit over here, folks, if you just bear with me just a little bit, because we know that v initial here is going to be 0. So what I'm going to do for you on Thursday, what we'll do on Thursday then is I'm going to go ahead and finish solving for this problem, but I would like you to think about then why it is then that this problem becomes very simple. We can solve for time. Why? Because the initial velocity becomes 0. So therefore, do we have the displacement? Sure we do. It's this one right here. And we have the acceleration along the y. It's that right there. We can solve for time. And so that's why with these projectile motion problems, folks, if you draw out the pictures and you have everything in front of you, okay, it makes it much, much easier to solve for these problems. And that what we'll do then on Thursday is we're going to go ahead then and we're going to take a look at this problem. We're going to finish solving for it. And then we're going to start on Monday when I see some of you folks at school in class, okay, which, wow, right? When I see you on Monday, what I'm going to do then is we'll talk about how we do that, what I will be doing on Thursday, what we will be doing starting the back in school, okay? But we'll get into centripetal motion at that point, okay? All right. Have a good day, folks, and I will see you folks tomorrow for the exam. Okay?